Okay, F-6, volumes of shapes with constant cross sections. Couple things to say up front to have in your head, especially when it comes time for test time. F6, F7, and F8 are three sections that are all about finding volumes. There are two types of shapes that we find volumes of in calculus. And these first ones, with full disclosure, I think they are, rather than being practical, real-world examples of finding volumes of things, they are finding volumes of things that we do because they're easy to do using calculus, relatively easy. So these shapes only exist for the fact that they are easy to find their areas using calculus. You have the big one? I'm going to steal the big one off you and give you the small one instead. So like the description of these shapes when we get to it in a minute is just, it's a weird description and they only exist because calculus. So nothing practical about these whatsoever, which is right up my alley. When math gets practical, that's when I stop liking it. This is sort of the opposite. This is fake practical for the case of math. Give me it all day long. I'm in. The first thing we need to do, though, before we can even jump into these, is talk about areas, just review some area formulas. In the descriptions of these shapes, we're going to say that the shape has cross sections, or the three-dimensional shape has cross sections that are some two-dimensional shape that we should know the area from geometry. So we'll review that first. You should be able to see, if you have access close by to one where the slats are taken out of it, that every face of this shape is a square. So this is an example of a shape. This is a shape that comes from this base, which is two functions. We'll see them in a minute on a graph. I don't know which way is right for you guys. It doesn't matter. So basically, we have a y equals function that makes the top. We have a y equals function that makes the bottom. And then the way the shape is formed is every cross section of this shape is a square, which means that the shape is taller the further apart the two lines are, because it's got to be a square. So whatever that base of the square is, then the height of the square needs to be too. So that's why this shape has this sort of curve like it. The closer the two lines are together, the shorter the shape ends up being. The further apart they are, the bigger the shape ends up being, because we took a two-dimensional shape and we put another two-dimensional shape on top of it that matched the dimensions of the distance between the two lines. So again, 100% made up for just calculus, the best thing ever. So let's review those formulas. Let's see how all this works. Easy one first. If a square has a base of b, the area of the square is b squared. There we go. All right. This next one is a little bit, it's not general, but it's a general idea. Sometimes, rather than telling you you have a square, they will tell you that you have a rectangle with a height that you could figure out if you know the base. So this example that I have here says you've got a rectangle where the height is half the size of the base, which would mean that this side over here is b over 2, which means that the full area is, base times height is the area of this rectangle. B times b over 2 works. I would probably say b squared over 2. But that's equivalent to b times b over 2. There's nothing special about the 1/2 there. This could be a rectangle with a height that's twice the base, and then you would have the 2 as a coefficient rather than something you're dividing by. I've even seen them where it's where you've had a rectangle with a constant height, and then you actually end up with just like a number times b, because you just have a number here and you don't have something with a variable in it. So you just kind of have to do the work on that one. A semicircle with a diameter of b. Do I want the diameter if I'm finding the area of the circle? No. I want the radius. So what's the radius of this semicircle? Yep. Yeah. So if r is b over 2, Thank you. So if our diameter is b, making our radius b over 2, what's our area? Yep, 1/2 pi b over 2 squared. Which you're in the process of what we're going to be doing, we're going to need to simplify. So this is all multiplication. So treat the numerators and the constants as a numerator. Treat the denominators as a denominator. So in our numerator, we have a pi and a b squared. So pi b squared. And we have a 2 from the 1/2 and 2 more 2's from it being squared. So we really have 2 times 2 or 2 times 4, pi b squared over 8. Cool. From easy to hard, isosceles right triangle with a base as a leg. What does the word isosceles tell us about the height of that triangle? I didn't hear you. It's same as the base. Yeah. I don't know if that's what you said or not. We'll go with that. That's what you said, right? Yes. And the area of a triangle is 1/2 base times height. So that's just going to be 1/2 base squared, or b squared over 2, like I had. So this actually ends up being the same formula as the rectangle from above. Just 2 different ways of cutting a square in half. Ooh. We took geometry, was our COVID class? No. Oh, okay. Yeah. Yeah. All right, so we have excuses. As long as we have excuses, we don't have Jaden here today, so you guys have to provide your own excuses. So, yeah. Right. Yeah. Online. Okay. Isosceles right triangle with hypotenuse as a leg. I'll say if you had to pick the one math that I would not want to have to teach, it would be geometry. But that's just from it being the one thing I've really never taught. So I don't have a dislike to it. It would just be like a whole new learning process. Anyway, so I just drew I got to do base times height, right? So we know the base, it's b, that's good. I don't have to mess with that. When I draw in a height, what happens to those 2 angles up there? They become 1/2 of what they were, which they were 90, 45, right? So we have a 45, 45. We have 2 45, 45, 90 right triangles. And each of those 45, 45 right triangles have a leg of b over 2. Oh, this one's easy. Right. And that's isosceles. I thought this one was going to be harder. This is the only hard one, I guess. I didn't do these before class. Do you get why I did that? If it's 45, 45, 90, I'm focusing on, I should really be doing this because I have a few people who might watch the video. So this is the triangle I'm focused on. It's got 2 45-degree angles, which make it isosceles, which mean these 2 sides are the same. This got cut in half when I drew in the height, and that means that this is b over 2 and that's b over 2. So I think, nope, slightly different formula. I was thinking this was going to be the same. No, it is. It is going to, can't be. We have base times base over 2, which is, so we have 1/2. I knew it was going to be different. Base times b over 2. So this one's going to be 1/4 b squared, or b squared over 4. I was clunking my 2 halves together. I'm like, it can't be the same as this one. Keep saying one of these triangles is going to be fun. Here comes the fun one. Equilateral triangle. Base is the B. Draw in the height. Split into B over 2 and B over 2. Same thing as the other one. That top angle was split. What was that top angle before I split it? If it was an equilateral triangle. Yes, thank you. Yeah, it's 60. Equilateral triangles have all three sides the same length. And because of that, they have all three angles the same angle measure. And then if they have to add up to 180, 60, 60, and 60. So you end up breaking those two 60s into 30s, which gives you our other special right triangle, the 30, 60, 90. So we, again, are focused on this triangle. The relationships between a 30, 60, 90 triangle, 30, 60, 90 degree triangle that you guys all have memorized are the side across from the 30 is S. The side across from the, that's not a right angle. Let's put a right angle sign in something that doesn't even, I can do this instead. There we go. The side across from the 60 and the side across from the 90 are what and what? No clue. 2S and S square root of 3. Oh, yep. Yeah, that's also pre-calc. Yeah, this is solidly both geometry and pre-calc. Special right triangles. No, not like this one. Yeah. It's really nice to go back and tell those guys, this is real. You do need to know this later on if you're planning on not just taking the easy way out and taking stats. So yeah, that's what we've got there. So in our triangle, we don't have S, we have B over 2. So what's this guy, S over S square root of 3 in our triangle? Yeah, S square root of 3 over 2. Basically, this triangle is half the amount that this triangle is, so everybody just needs to get divided by 2. So S square root 3 over 2. All right. Which makes our area of the bigger triangle. I didn't say that in the last example, but we're trying to find in all of these the area of the bigger triangle, the base, which is B, times the 1/2 that I forgot to say, times the height, which is, let's use a B, not an S, boom, times B square root of 3 over 2. So we have A equals 1/4, B, I guess I could say root 3 over 4, B squared. Numerators and whole number / variables get multiplied. Denominators get multiplied. If everything's all multiplication. Algebra. All right. Okay. So at least we have a reference sheet for this. I will say on the AP test, their goal is not to test your prior knowledge of other classes to a degree that's unreasonable. I mean, you do need to know that a rectangle is base times height. So you can't avoid testing other classes. So I don't think that like you would expect to see a question where they actually made you kind of remember this formula. And you have them as reference for when you do anything that you see later in the packet. So that's the goal of this page. Now on to the real stuff. Today we are finding volumes of shapes that are described as shapes where we know the cross section. This sentence comes from experience. We're going to be doing shapes where you're going to see one of two key words. You're either going to see cross-section or you're going to see rotation, okay? This formula is the simplest formula you really could think of, because all we're going to do is integrate the area formula that we have on the first page. So these area formulas are the thing that we're going to integrate. Next week, when we start looking at these rotations, circles are going to be heavily involved, right? If you take something and rotate it, that just naturally makes a circle. Those formulas are going to have pi built into them because of that reason. Word of warning, know what you're doing and think before you start writing things down and end up using the wrong formula. Both of these formulas are the same. It just depends on whether they say that the cross sections are perpendicular to the x-axis or perpendicular to the y-axis. This is not like the problems we did on the other page where you can get the same result no matter which way you do it. They are going to tell you your shape is going to be different if you do it x versus if you do it y. So they're going to describe the shape and literally tell you which one to do. And luckily, it's, you know, if you're perpendicular to the x-axis, then it's going to be in terms of x. If you're perpendicular to the y-axis, you're going to be in terms of y. Okay, so let's get a little bit of an idea more of what's going on. There's a couple visualizations on this page, and the piece that you have on your desk in front of you is the thing that's here in the first section. It literally, they kind of pick the same two formulas. What happens in all of these, whether it's the rotations or these ones, is we've taken the geometric formula for something, and one of those things is changing. So like, these are all based on the area of a prism or a box, okay? But what's happened is, as the little sides on here that you can see, your front looks like the front of a box, your back looks like the back of a box, but you see that these are kind of diagonal, right? They aren't even perfectly diagonal. This is actually a curve. That's where the calculus comes into play. So one of the things in that formula, which if it's the volume of a box, that's just length times width times height. One of those things is replaced with the dx or the dy. So in this case, the things that aren't replaced are the length and the width. So the length and the width, we are just finding the area of a square. That's why we're integrating area, but it is the height. It's the going back and forth. I guess in the way of looking at this way, you're more thinking of depth. That's what's getting replaced with the dx. So because our shape changes this way and we don't just have a straight box going back, that's where we're kind of integrating. So when you put this shape, a shape like this, and you're sort of looking at it, everywhere along the way, the base of those rectangles is your upper function minus your lower function. So at one spot along the way, you can take the upper function, which kind of isn't shown because it's covered up with the shape, and subtract the lower function to get that length right there, right? And if you look at the shape, that should sort of match too, right? How wide is my rectangle? Well, it's the upper function minus the lower function. Which means that the thing that you are not integrating, like the thing that you're that's not the dx, is that square, and it's got a base of f of x minus g of x, and because it's a square, it's got a height of f of x minus g of x. So the area of any given one of these squares along the way is just f of x minus g of x, but squared. That is a formula that if I gave you an x value, I said, here I am, this is the x value, it's this number. You could plug it into this formula and square it, and you would find the area of that exact square you're looking at. Does that make sense? Okay. And then integrating is taking the fact that we have those squares, and unlike a box where all those squares would be exactly the same size, in this case, every single square is different, right? Yeah, there's a couple on layer that might be the same. That's not what I'm saying. But the size of that square changes every single time you move your x. And that's what the integration takes care of. So when it comes time to finding the volume of this shape, this is area, volume is just going to be integrating that area. I'll even make this a of x. That's how we're going to integrate it. And again, the only thing that's going to change is we're going to change the cross sections, which means we're going to use a different formula. But that's why we did the legwork on the front here. Wherever you have that b in the front, you're just replacing it with f of x minus g of x. So when we have a semicircle, what's going to end up happening is the whole bottom, the f of x minus g of x, is now the diameter of each semicircle. So we're going to have to take, just like we did before, to find the radius, that's just going to be f of x minus g of x over 2. And then we're going to do half pi, that radius squared. So just like the front, half pi f of x minus g of x over 2, because it's the radius, but squared. I will, like I did above, call this a of x, just letting us know that that area is different based on which x value you're at. Which again, just like the front, is going to give us 1/8 or pi over 8 times f of x minus g of x squared. And that comes from squaring the 2 in the denominator and multiplying it out by that 2 there. But then again, if I want to find the volume of this shape, and I think this is why I say, these are shapes designed for calculus, I'm just going to take that thing I figured out and integrate it. The calculus part is the nothing of this all. It's the getting to the calculus part that's the work. So this is the integral. Actually, yeah, yep. So v, not v of x, because v is a single thing. The volume of this shape, is just the integral, and I'm leaving off the limits because I'm just being a little bit informal here, of that a of x dx. That's how I wrote it up there, yeah. The single volume, the answer to the question, what's the volume of your shape, is the integral of that area function. This is a shape made up of a bunch of semicircles, but all of those semicircles are different. That's what we need integration for. And then this is the same thing. And in this one, I'm just going to go back to our formula. I'm not going to derive it this time, because what I'm saying is just take whatever you have for b in the front page and replace it with f of x minus g of x. So for our equilateral triangle cross sections, we said 1/4 b squared. So here, any given area is 1/4 f of x minus g of x squared. And the volume is just the integral of that area. So with cross sections, one of the two things we're going to do. The thing that we always have to differentiate once we get them out in the wild and we don't know which problem it is, when you have cross sections, you find that area formula. The formula that gives you the specific area of the specific cross section at whatever x value you're at, and you integrate it. And of course, we'll have to know a starting point and an ending point. Yep, thank you. It was root 3 over 4, right? I looked at the isosceles. That was the only difference? Or no? Yep, thank you. I'm glad we caught it while I was going over it. Yep, I looked back up at isosceles. That was the one in the middle, but this was the equilateral. All right. Cool. One of the things that, because it is f of x minus g of x, a lot of these end up either being calculator active or just write the integral type problems. So, which integral represents the area, the volume, things like that. All right. So let's do a couple problems. This shape that we have here in problem number 1 is the shape that you're looking at. Make it let's see if I can do it. Oh, that's too big. No, it was behind me. That's too big. It's about half the size. Close enough. A little bit smaller. So yeah, so this shape was based. This was fun my first year trying to figure out how to do this. I got a lot of extra Bitman time in my life because he has the 3D printers. So yeah, and 3D printing software is not designed to do this because this is super impractical. So it was fun. Anyway, so this shape is based on this. So this is the square root of x squared and sorry, wrong. I pointed to the wrong one. The square root of x and x squared. Those two things meet at 0, 0. They meet at 1, 1. So similar to what we were doing yesterday where we were finding the area, now we're using that area as a base and building our shape like that. They want to know what the volume of this solid is. The way we would figure that out is we would integrate the area. Any given cross-section is a square with a base that is f of x minus g of x, where f of x is the upper function. So my area in this case is f of x minus g of x squared. The upper function is the square root of x. The lower function is x squared. Right? So if I wanted to find the area of the cross section at 1/2, I would just plug a half into that formula. How about that? Yep, thank you. Thank you. Cool. All right, so to find the volume, we need to integrate from the beginning to the end, which is 0 to 1, x equals 0 to x equals 1. That area formula, so the square root of x minus x squared dx. And what do we have to do to actually integrate that? What? Yeah, we do need to FOIL that. There is nothing you can do with the square root of x minus x squared squared. If you start trying to use the power rule as is and do silly things like that, that's a good way to get the wrong answer. There's no u sub that works because your only possible u would be this, and this has a derivative that is nowhere else inside of it. There's just nothing else there to be there. So yeah, you do need to FOIL this out. Again, this is kind of a good show as to why a lot of times these are either calculator active or which integral does the thing I need it to do. So square root of x times square root of x is good. Now we've got to do the inners and the outers. They'll both be the same. I've got to multiply x squared by the square root of x. X to the 5/2. X squared times x to the 1/2. 4 halves and another half make 5/2. But there's 2 outers and inners, right? I'd have to do that twice. So I'm going to write minus 2, x to the 5/2. I erased my x squared. And x squared but squared is x to the 4th. dx. Antiderivatives. Easy one first. X squared over 2 minus 2 x to the, yep, times, yep, cool, plus x to the 5th over 5. But luckily evaluated between 0 and 1. Because the 0 is going to be 0, right? And the 1 gives us 1/2 minus 4/7 plus 1/5. What's that? That is a number. I agree. It is. It's got 70 as its denominator. So 50 minus 40. Nope. 35 minus 40. Plus 14, yeah. I don't know, maybe it's blanket on that one. So hopefully we end up positive here over 70, which we do. 49 minus 40 equals 9/70. That might feel kind of small, especially when you've got this big thing in front of you. But what you need to remember is this would be cubic units. So 1 whole cubic unit would be a block that was 1 by 1 by 1 out this way. And keep in mind, even at its fattest, you're not even coming out a full unit, because in order to come out a full unit, you would have to have your upper function at the top, your lower function at the bottom. So you are saying 9/70 of 1 cubic unit, which is a lot bigger than the shape. 1 cubic unit would be a box, this wide and about the same amount of tall. So you're only filling 9/70 of that box. Okay. All righty. Some of this is a little bit repetitive. That's okay. Volume of a solid with known cross sections. We already said this. This is just the integral from A to B of the area formula, where A of X, thank you, is the area of a cross section. All right. So if it's a square, it's just going to be F of X. It's just going to be, I forgot how we had this written. It's just going to be S of X squared, where S of X is F of X minus G of X. I didn't do any editing to this page. Yep. And if it's a rectangle, it's just going to be whatever H is, and this is kind of a problem-solving thing, times F of X minus G of X. He's not even consistent with the way he wrote his notes. We've reached the end of the year set of notes where a lot of them, at least on my part, are a little more phoned in than they have been in the past. And I'm just going to use this without editing it. So sometimes, the height, we saw this in that middle example from the very first page where I said height was half the base. So that would end up just making this 1/2 F of X minus G of X for your height. So yeah. All right. Number 2. This is like almost an anti-example, because we're going to see that it's the exact same thing, but this is usually not the case. This shape we have here has diagonal symmetry. So if we were to consider our cross sections against the y-axis, so when I put this shape up here, you'll notice that my boxes are going straight up and down. That's what perpendicular to the x-axis means. If I built a shape where they went in the other direction, in general, that's going to give you a different volume. So if my cross sections were horizontal instead of vertical, that's going to give you a different volume. But in this case, because of that symmetry, it's actually not going to. And I'll show you why. Because what we would have to do here is we don't want A of X, we want A of Y. And our base is F of Y minus X minus G of Y, which, just like the other section, we're thinking further to the right versus further to the left when we're thinking upper and lower functions. But taking the two formulas that we had, which were y equals the square root of x and y equals x squared, there's one step ahead in my brain there. Taking those formulas and putting them in terms of x, if y equals the square root of x, then what does x equal? Yep. And if y equals the square root of x, then what does x equal? Square root of y, yeah. So it does turn out that when you end up with the same two functions, it's just your x and your y have now swapped places. So when we go to do our area formula, we're now looking at the y values. So we are integrating again from 0 to 1, but that's because this shape goes from 0 to 1 in both x's and y's. Our area formula is f of y minus g of y. Y equals this, our upper function, because we're thinking in terms of left to right, is y equals x squared. That makes our upper function x equals the square root of y. So it still ends up being the square root of y upper function minus, this is now the lower function because it's further to the left, y squared. That is the base squared, puts a 2 there, dy. That integral is exactly the same integral we did in the previous example, with a variable change. Kind of speaks to the fact that the variable inside an integral is a dummy variable. Its letter means nothing to the actual solving of it. So same answer as we got before, 9/70ths. Cool. All right. All right, so let's do the third example and then hopefully have a couple minutes to try a couple on our own. So new example, base of a solid is bounded by three functions, y equals x cubed, y equals 0, and x equals 2. Find the volume if the cross sections taken perpendicular to the x-axis form a rectangle whose height is 2 times its width. So this is going to be just a simple example where when we go to do our area, instead of having base squared, the height was twice the base. So when you multiply those two things together, you get 2b squared. Make sense? Yeah. Okay, so x-axis, that means we're going to write dx. That's nice to remember with these ones. So we're good to use our functions as is. We are looking for any given base to look like this. If I really had this shape right here, this thing would stick off the board as much as my fingers are across from each other. This thing would actually get pretty big as you got to the end, because as far as my fingers are apart here, it would now be sticking out this far. But that's just going to be f of x minus g of x, and f of x is x cubed. So my area is 2 f of x minus g of x squared, because of the area formula, which is just going to be x cubed minus 0, because we're just butting up against the x-axis, but squared. So how about x to the 6th? 2x to the 6th. Yeah, I lost it in this spot too. Yep, thank you. That was an equal. That was a 2. There we go. 2x to the 6th. Boom. So this time, our x values go from 0 to 2. So we need to integrate from 0 to 2 of 2x to the 6th. I'll bring the 2 out front. X to the 6th dx, which is x to the 7th over 7, but times 2, evaluated from 0 to 2, which is really just 2 times 2 to the 7th over 7 minus 0. 2 to the 8th. 4 to the 4th. 16 squared. 256 over 7. Or 2, 4, 8, 16, 32, 64, 128, 256. I got 8 fingers up, so I'm right. exciting, right? A shape that doesn't really exist in real life has a volume of 256 sevenths. This is what you signed up for. All right. What happens if we take those? Oh, this one's actually a little bit easier. But yeah, so we're going to do a different height. We're going to take perpendicular to the y-axis, and we're actually going to have a constant height rectangle. So this shape's height doesn't change based on the spot you are on the lines. It is always just 6 units off. This makes for a much easier problem. You still need calculus for it because each cross section does have a different width, but their height is locked in. So in this case, our area formula is just the base times 6, so 6 feet. But since our cross sections are perpendicular to y, we need to have a dy here, which means that all of our functions need to be in terms of y. So we'll start with y equals x cubed. We can't do really anything with the numbers. We'll see kind of how they work differently in this one. In going in terms of x's, y equals 0 is actually one of our functions. And then x equals 2 was our bounds. Those two things are going to switch roles when we go in the other direction. So we'll see that as we go through this. Oop, I erased the wrong thing. So perpendicular to the y-axis, I need to do dy. So I'm going to put that down here. My area is 6 f of y minus g of y dy. As I'm looking from left to right, what's my upper function? Which one's further to the right? Yeah, x equals 2. That upper function is the horizontal line, x equals 2. So our area is 6 times 2 minus, what's our lower function? The other one, which is, we only have 2 choices, and one of them is, it's y equals x cubed. But the problem is we can't put x cubed there, we need to put y. Yes, the cube root of y. So y equals x cubed means that x equals the cube root of y. So we've got 2 minus the cube root of y dy. So yeah, so in terms of perpendicular to x, that 2 is just a bound. But in terms of perpendicular to y, that 2 is a function. It's actually the upper function because it ended up being a barrier to where the kind of shading went in the direction we were looking, left to right. So we need to integrate this time from 0 to not 6. 8, yeah. Yeah, so we're going in terms of y, so our integration bounds need to be y values, and this shape exists completely between y equals 0 and y equals 8. So we'll integrate from 0 to 8. The thing we said we were going to integrate, which was 6 times 2 minus root 3 of y, third root of y, which is 6 times 2y minus y to the, but I'm integrating. 4/3. Yeah, I'm integrating, right? I changed 2 to 2y. I have y to the 1/3, so I have to add 1 to that. I get y to the 4/3, and then multiply by 3/4. Yep. And I've got to evaluate that from 0 to 8. 8 is okay, 0 is good because 0 times 0 to any power is just 0. So we just have 6 times 2 times 8, I know that, minus 3/4, 8 to the 4/3 power. So I've got to figure out, remember, root first. We take the root first, then we raise to the power. So the third root of 8 is 2. I meant to ask for that, but I said it, so whatever. The third root of 8 is 2, and now I've got to multiply 2 by itself 4 times. But I know 2 times itself 3 times is 8, so 16, yep. Yeah. So we end up with actually 6 times 16 minus 3/4 of 16. Yep. So 6 times 4 is 24. There you have it.